Hi everyone and welcome back to our channel. We have discussed in previous videos how 5G has the potential to transform our mobile technology related experiences. However, it also has the scope to transform experiences beyond those powered by smartphones. 5G connectivity is poised to bring significant developments to virtual, augmented and mixed reality, collectively known as extended reality or XR. XR is an umbrella term for all of the immersive technologies. The ones we already have today, augmented reality, AR, virtual reality, VR, and mixed reality, MR, plus those that are still to be created. All immersive technologies extend the reality we experience by either blending the virtual and the real worlds or by creating a fully immersive experience. In augmented reality, virtual information and objects are overlaid over the real world. This experience enhances the real world with digital images, text, and animation. One can access the experience through AR glasses or via screens, tablets, and smartphones. This means users are not isolated from the real world and can still interact and see what's going on in front of them. The most well-known examples of AR are the Pokemon Go game that overlays digital creatures onto the real world, or Snapchat filters that put digital objects such as hats or glasses onto your head and face. The South Korean mobile operator LGU Plus has an augmented reality dance-off application that you can use to show how well you dance with their well-known pop star Chung Ha. The link of the video is available in the slides that you can download from our SlideShare channel. In contrast to augmented reality, in a virtual reality experience, users are fully immersed in a simulated digital environment. Users must put on a VR headset or head-mounted display to get a 360-degree view of an artificial world that fools their brain into believing they are, for example, walking in Jurassic World, swimming with whales, or stepping into whatever new world the VR developers have created. The gaming and entertainment industry were early adopters of this technology. However, companies in several industries such as healthcare, construction, engineering, the military, and more are finding VR to be very useful. Here is an example of virtual reality from an advert by the Japanese operator NTT Docomo. As you can see, VR has the power to transport you to a far-off destination as if you were really there. It's quite possible that in the future, people will watch sports using their VR headsets. In mixed reality, digital and real-world objects coexist and can interact with one another in real time. This is the latest immersive technology and is sometimes referred to as hybrid reality. It requires an MR headset and a lot more processing power than VR or AR. Microsoft's HoloLens is a great example. It allows you to place digital objects into the room you are standing in and give you the ability to spin it around or interact with the digital object in any way possible. Companies are exploring ways they can put mixed reality into work to solve problems, support initiatives, and make their business better. Here is an example of mixed reality using Microsoft HoloLens. As you can see, multiple people can interact with real and virtual information to decide on the best course of action. There are many practical applications of XR. For example, in retail, XR gives customers the ability to try before they buy. Watch manufacturer Rolex has an AR app that allows you to try on watches on your actual wrist. And furniture company IKEA gives customers the ability to place furniture items into their home via their smartphone. For training, especially in life and death circumstances, XR can provide training tools that are hyper-realistic that will help soldiers, healthcare professionals, pilots, astronauts, chemists, and more figure out solutions to problems or learn how to respond to dangerous situations without putting their lives or anyone else's at risk. In the case of remote working, workers can connect to the home office or professionals located around the world in a way that makes both sides feel as if they are in the same room. In the case of real estate, finding buyers or tenants might be easier if individuals can walk through a space and decide if they like it, even when they are in some other location. As an early adopter, the entertainment industry will continue to find new ways of utilizing immersive technologies. In the case of marketing, the possibilities to engage with prospective customers and consumers through XR will have marketing professionals pondering the potential of using XR for their company's advantage. XR will serve a broad spectrum of roles in daily life and impact everyone. It will be applicable across ages, genders, and activities. Some examples are: XR will transform how children learn and play. They will chase VR characters, have holograms for teachers, and experience immersive gaming. Tourists often have visual and audio guides, but with XR they will have VR aids that can show them how historical sites originally looked and immerse them in history. XR means families will be able to communicate as if they are in the same space with lifelike conditions. In professional fields, engineers, architects, etc. can use XR to collaborate on design and improve efficiency. People will be enthused by virtual trainers who will work out with them to improve health and fitness. Disabled individuals can take part in experiences that might be impossible or unsafe for them in real life. They can run, ski, ride bikes, and climb mountains. The possibilities are endless. Just in case you were wondering how headsets look today, here is a look at the most popular ones from the presentation by Jensler. These are the concept AR glasses from Qualcomm. They clearly show all the different types of sensors and cameras that are required for proper AR glasses that are supposed to work as shown in concept videos. One of the big challenges would be to have 4G, 5G connectivity and battery that can last 2 to 3 hours. It will take a few years before we have a proper prototype of this. Another concept worth mentioning up front is that ideally we are talking about 6 degrees of freedom when we are talking about XR, as opposed to 3 degrees of freedom. 6 DOF allows the user to be completely immersed and be part of the story as compared to 3 DOF, where the user can just watch. Coming on to 5G. You may have seen this requirements slide from us in many different videos. When we were talking about XR, we are talking about high data rates as well as low latency. You can see in the picture, the requirement for AR/VR is right in the center. The 3GPP Technical Specifications Group for Services and Systems Aspects is known as SA. SA1, which is responsible for finalized service requirements for 5G, is called New Services and Markets Technology Enablers, also known as SMARTA. These requirements are documented in the Technical Specification 22.261, Service Requirements for the 5G System. VR aspects are addressed under Efficient Content Delivery and Low Latency and High Reliability sections. The requirements on the data rate is 250 Mbps. These are requirements on motion to sound and motion to photon latencies, and on audio-video synchronization. A study on virtual reality between April 2016 to June 2017 investigated VR use cases, and they are documented in 3GPP TR 26.918 for the relevance of VR in the context of 3GPP. By collecting comprehensive information on VR use cases, existing technologies, and subjective quality, the TR attempts to identify potential gaps and relevant interoperability points that may require further work and potential standardization in 3GPP. The TR primarily focuses on 360-degree video and associated audio, which supports 3 degrees of freedom. 3GPP TS 26.118 Virtual Reality Profiles for Streaming Applications that was released as part of 3GPP Release 15 provides technical specification for VR streaming services. As part of that, it provides a definition of client architecture and API for VR streaming services, a set of operating points covering the large range of device capabilities from cardboards to high-end tethered HMDs, definition of media profiles, mapping of operating points to dash delivery. System metadata is added to support rendering of 360 experiences on 2D screens, including the aspects of rendering without pose information. XR use cases, including AR, are further discussed in detail in the 3GPP SA4 study item Extended Reality in 5G, which is TR26.928. The following classification of use cases is identified in the document. Offline sharing of 3G objects. Offline sharing is used for sharing 3D models, objects, and 3D mixed reality scenes among users. Real-time XR sharing. Video chats are captured using 3D models of people's heads, which can be rotated by the receiving party. Multi-party VR conferences support the blended representation of the participants into a single 360-degree video with a pre-recorded office background. Some of the conference participants may also be overlaid on an AR display. XR multimedia streaming. The typical media streaming experience is enhanced with the capability of 6 degrees of freedom within a scene. 6 DOF motion and interaction are allowed by changing the viewer's angle within the scene and by head movements with a head-mounted display, HMD. Online XR gaming, multiplayer VR games will allow remote people to play and interact on the same game space. Users can change their in-game position by using controllers and body movements. It is possible for a game spectator to take 2 possible views, the player's view and the spectator's view. Interaction between a spectator and the players is also envisioned. Industrial services. One of the use cases considered by 3GPP in this area covers an AR-guided assistant at a remote location for augmented instructions and collaboration. It requires AR glasses. A remote assistant is guiding a local person to perform maintenance on an industrial machine. The remote assistants can see in real time through the local person's AR glasses the local environment and the machine to be repaired. Part of the repairing instructions are sent as overlays to the AR glasses. XR mission critical. In this use case, a team in an indoor space is equipped with mission gear that is connected to a centralized control center. There may be more than one device included in the mission gear, such as AR glasses, a 360-degree helmet-mounted camera, a microphone, a binaural audio headphones, and other sensors. A control center conference server performs the role of mission support by providing XR graphics such as maps, texts, location pointers of other team members or other objects, people in the surrounding area, etc. The mixed audio of the team members as well as audio from control center is also delivered to the team members to aid team communication and coordination. One or more drone-mounted cameras may also be used, which can be controlled by the control center or one of the members of the mission team. XR conference. This use case envisions an XR conference with multiple physically co-located remote participants using XR to create telepresence. The shared conference space can be 1. A physical space that is shared by local participants and sends an immersive stream to the remote participants, or 2. A virtual space that has the same layout as the physical space so that the physically present local and remote participants have a similar experience while moving in the space, for example, captured via a 360-degree camera, and 3. A virtual space that is retrieved from an application server. In any of the 3 options, the conference space might be extended with other media objects, for example, a presentation video retrieved from an application server. Spatial audio multi-party call. This use case envisions an AR multi-party call. Each party can see the other parties using 2D video streams captured by the front-facing camera of a mobile phone. Alternately, they can be displayed as avatars, for instance, when the pair of AR glasses are used at each party. Each party hears the spatial sound audio with the audio of the other parties originating from where their avatar video is placed on the display. Motions such as head turns are tracked to create a realistic impression that the audio is originating from that virtual direction. Extended reality devices are of different form factors, as shown in the picture. These form factors may differ in processing capabilities, communication types, and power consumption. 3GPP TR26.928 has a detailed discussion on these. We will discuss some of them here. The majority of VR and AR devices are head-mounted displays or HMDs. In AR, the display is usually transparent and digital information is superimposed onto real-life objects. In VR, the display is not transparent and only virtual information and images are displayed in front of the wearer's eyes. A smartphone, defined as XR5GP1 device type, may be used for both AR as well as for VR, together with something like cardboard. In both cases, typically an XR engine or runtime is available to support processing of sensor data, viewport rendering, as well as SLAM processing. SLAM stands for Simultaneous Localization and Mapping. In the case of XR5GP1, the 5G modem and all media XR processing is integrated in the device. Power consumption of such devices is important, but not ultimately critical due to the onboard battery. VR HMDs typically provide a large field of view, stereoscopic 3D imagery, as well as rotational, translational, and positional tracking for full 6DoF experiences. For VR, the device types identified are shown as XR5GV1 to XR5GV4. XR5GV1 is a simple wired VR display, and such device types are commonly available today. They only include sensors for tracking as well as display. The remaining processing is done on a remote device, for example, a puck or a smartphone. XR media processing, connectivity, and power supply are provided through wired tethering. XR5GV2 is a simple VR display with wireless connectivity. They are not yet available as of today. XR5GV3 is a smart VR viewer with wireless tethering. They are also not yet available. XR5GV4 is a standalone VR HMD, and these kinds of devices are already available today. For AR glasses, design constraints are significantly more important. In particular, design constraints apply in terms of sleekness, weight, and power. The processing power is expected to be low to avoid battery consumption and thermal dissipation. Wireless AR glasses are commercially compelling. AR is typically associated to using glasses, also referred to as optical see-through. However, AR experiences may be achieved using HMDs with video see-through functionalities. 3GPP has identified the following types of devices. XR5G A1, which is a simple wide AR wearable glass. Such devices are already available today. They include a minimum number of sensors, possibly cameras for AR localization, as well as display. Power, XR processing, and connectivity is supplied from an external source. XR5G A2 is the same as XR5G A1, except for the wireless connectivity. Such device types are not available as of today and are still some time away. XR5G A3 is a smart AR HMD with video see-through. These are very similar to XR5G V1 types of devices, but by having cameras projecting the real world on the screen, the VR device can operate as an AR device. Such device types are already available today and are an initial entry for AR and MR applications. XR5G A4 is a standalone AR wearable glass which is not available as of yet. XR5G A5 is a smart AR wearable glass with wireless connectivity. These types of devices are still quite far away. Here is a summary of all the XR device types from 3GPP TR 26.928. You may want to download the slides from our SlideShare channel to look at later on. This slide shows the 5G XR functions integrated in a 5G system. If you haven't seen our 5G core tutorial, please check it out as it would help you understand this. Here, the 5G XR client is a AUE internal function dedicated to 5G XR services. 5G XR AF is an application function dedicated to 5G XR services. 5G XR AS is an application server dedicated to 5G XR services. Functions in trusted data networks are trusted by the operator's network. Therefore, application functions in trusted data networks may directly communicate with all 5G core functions. Functions in external data networks may only communicate with 5G core functions via the network exposure function or NEF using N33. Edge computing is a concept that enables cloud computing capabilities and service environments to be deployed close to the cellular network. It promises several benefits such as lower latency, higher bandwidth, reduced backhaul traffic, and prospects for several new services as indicated in the 3GPP SA1 study on application architecture for enabling edge applications, which is detailed in 3GPP TR 23.758. Edge applications are expected to take advantage of the lower latencies enabled by 5G and the edge network architecture to reduce the end-to-end application level latencies. Edge computing is a valuable enabler that should be considered to help 5G systems achieve the required performance to enable XR. The end-to-end traffic requirements from an XR end-to-end architecture can be broken down into requirements on the traffic between the XR edge server and the 5G system backhaul, and the requirements of the traffic on the 5G system. The edge server for XR can be owned by the 5G operator or a third party and hosted by the operator or a third party. If the edge server is owned and hosted by the operator, then the requirements of the traffic between the edge server and the 5G system is well understood, and consequently, the definition of the requirements of the XR traffic on the 5G system is easily accomplished. If the edge server is owned and/or hosted by a third party, it is anticipated that a service level agreement between the third party and the 5G operator can define the terms based on which the requirements for the traffic between the edge server and the 5G system can be defined. An example of set requirements on XR traffic is shown in this table. The requirements depend on the XR use cases and the end-to-end architecture option. Two examples are described in the table. XR streaming use case with device-based architecture, XR gaming use case with generalized XR architecture. As described in the table, the XR streaming use case with the device-based architecture is expected to be carried as transmission control protocol traffic in both uplink and downlink. The uplink traffic can be a HTTP request or optionally updates to the user's pose at a slow timescale, for example, once every 500 ms. The download traffic is XR streaming traffic, which can be in one high resolution for all 360 degrees or in a high resolution in the direction of the last known pose, and at a low resolution in all other directions. The throughput requirement can be reduced by sending the high resolution views only in the direction of the known pose and sending the low resolution views in all other directions. This is another example set of requirements from GSMA white paper on 5G use cases for verticals China 2020. It's been provided as a reference. This presentation won't be complete unless we look at some challenges with XR today. The first is the form factors and affordability. As you can see, the form factors are still quite bulky today and they are not necessarily cheap. For these to be mass market, we are looking at sub $200 devices, which are quite light and sleek. The second challenge is that even though small processors have enough computational power available today, it's still not enough for XR. For XR to really succeed, a lot of processing power would need to be available on the devices, but they shouldn't consume a lot of power themselves. This challenge may well take a long while to solve. The final challenge is latency. 5G definitely helps here by reducing the latency significantly, but 5G alone won't help. There is definitely a need to move to newer architectures that involve a lot of edge. We will see these start coming from this year onwards. Here are some references for further reading on this topic. We hope you found this presentation useful. This is a complex topic. There is a lot more that could have been included, but we didn't want the video to be too long. Anyway, any comments or feedback are very much appreciated. See you next time. Thank you.